Okay. All right. Okay. So good day, everyone. Welcome to week 6 of Saturday's course 8. Sure, you guys have been having fun learning about the past 6 weeks too, since started week 0. And I hope you guys have been picking up with your assignments also. Today we have Kenechi Dukor as our instructor. He is the co-organizer with us here at School Takers. And he is also a robotics master student at the Northeastern University. Hopefully I got that right. So yeah, he's doing work around robotics, grasping and manipulation using reinforcement learning and computer vision. And he's a veteran tutor, like Pedro said, so I'm sure you guys will have a wonderful time. One thing to note also is we've not been getting as much feedback as we were getting by like the third lecture. So things sort of dropped down to like the initial condition. So I hope that everyone on this call takes some time to fill the feedback form. Of course, you probably don't want to fill it too early, but as time goes on, maybe in like the last 45 minutes or 30 minutes, we'll always be sharing the links, right? But please make sure you look for the feedback form and then fill it. Of course, we also do the same for the attendance, but you guys are typically doing that one. So we love your attendance, but please also love your feedback. And yeah, if you have any, thing you want us to put in mind as we complete the picture tutors, that is the best way to do so. So please make sure to fill the feedback form. It will help all of us. So I will now leave the floor for Kenechi, and I hope you guys have a great time.
Okay, thank you. Hi, everyone. The tradition is that I should turn on my video. Maybe I'm shy. So you guys, you can unmute or don't feel shy or feel intimidated or feel I'm just like everyone. I'm also learning. So feel free to unmute, speak. I like it when the class is very, very interactive and we're all learning together, right? And pardon my voice, it's quite early here, so yeah. So just before I start, right, I would like maybe to hear from one or two people. I know we are out of time. I have like 2 hours, but maybe 1 or 2 people tried. I want to kind of get an understanding of what they've learned from the previous lectures, how it has been so far, what they hope to learn in the coming lectures. Maybe 1 or 2%, and I can pick randomly if one person does not nominate himself in the next 2 seconds. Okay, Tope's mic is unmuted. So Tope.
Hello, can you hear me?
Yeah.
Oh, okay. Hello, everyone. Let's do the first week. We started with statistics, Python, starting what we do, different data formatting like that. Last week we worked with databases, relational databases. So these are some of the things we have discussed. Yeah, it's been calm so far. I think these are some of the things I do. So still looking forward to some of the other things. I don't know. But yeah, so far for me, it's a calm and super simple.
Okay, nice.
What am
Thank
I
you.
looking?
Okay, yeah. What are you looking out for next? Yeah.
So I'm hoping at the end of the day we publish a paper or something. I don't know how possible that is, but let's see. I hope that that is part of somewhere in this thing that we write a paper and then we find somewhere to publish it.
Okay, nice. So I can pick randomly next. Just one more person. Montserrat.
Oh, good morning, everyone.
Right,
Can you
good.
hear me?
Yeah, I can hear you.
Okay. So for me, this course has really been roadmap I really need to become a data scientist. I've been learning machine learning and I've just been learning everything now. This one is like giving me the roadmap, like what I need to know, what I need to know, what I need to become a better person. So that's just it for me. This I've been enjoying the process.
Okay, thank you. Okay, thanks. So I'll go right in. So we have quite a lot of things to cover. I do hope we can cover it all. I tried as much as possible to make it simple, straightforward, right? No too much. Permit me to use the word not too much serene, right? So let me know if you can see my screen. Can you all see my screen?
Yes, we can see it.
Okay, so let me turn off my camera. My face is not important at this point in time. Thank you. Except you want to see my face, just raise your hands up and you'll see my face again. So like I said, I would want the class to be interactive, right? I was told that there's really no like lab for this for this class, or really it would make sense if everyone kind of gets their hands dirty with this aspect of the course, because think of it as linear algebra is very, very fundamental to a whole lot of things. In our opinion, is even fundamental to life, how we move around, how we interact with our environment, right? Linear algebra is very fundamental to it, and you tend to find linear algebra in different disciplines, different aspects of life, right? In computer science, you have linear algebra. In physics, you have linear algebra. In economics, you have linear algebra. In actuarial sciences, you have linear algebra. And linear algebra pretty much makes sense out of data, makes sense out of the data you're trying to kind of manipulate or transform, really. So let's kind of pay attention, right? Some of the things you'll do here are things you'll forever keep doing in your machine learning journey, right? Some of you might be familiar to the concept of linear algebra, so this might just be like a refresher for you, right? So I have pasted a link in the chat. So you'll see it's a tiny URL. It's a link to like a Colab notebook. So in the course of the lecture, we will have something like a breakout session, not not a typical breakout session, right? But you'll pretty much have to go to Colab to make sense out of what you've pretty much just seen on the slide, right? But we'll be doing it together. So we're pretty much going to, oh, sorry, this whatever I say is not updated. Please ignore this, right? I'll just go straight into it. So I kind of, this is a bit late, but yeah. Okay, so the introduction, right? So linear algebra, just like I had said, right, in the beginning, it's a branch of mathematics, really, that finds itself in different aspects of our lives, right? Wherever you find linear equations, wherever you find linear functions, right? And in linear algebra, things are most times represented as vectors and matrices, right? And in more complex considerations, right, where in mathematics, right, you begin to consider things like groups, rings, fields, but these are some abstract stuffs that we aren't really bothered about in this class. And please stop me if you don't understand anything I'm saying, right? My job here is not to confuse you, right? It's to make sure you guys understand everything. So feel free to unmute and just say, hey, Kenechi, stop. You're saying rubbish. I don't get what you're saying. Yeah. Cool. Right. And in general, right, most times this is what you see, right? This kind of equation where you have a1 x1 plus an xn is equal to b, right? Where you're having a linear transformation of x, right? When it operates on an a transpose to give you a vector b, probably vector b in the transformation is pretty much the a matrix you have. So again, it's all gibberish, right? But we are going to make sense out of everything I'm saying, right?
Hi, Kenny. Can you hear me?
Yeah, I can hear you. Can you hear me?
Okay, please. I wanted to ask if you can actually drop this slide.
Oh, seriously? You don't have the... Oh, give me one sec. I'll do that now. Just give me 1 second. I'll share it. Okay. You are. Someone is writing on my screen now. Okay, so I put the slides on the chat. Can you also I'll put it on Discord. Okay, cool. Are we all okay? Can I move on? Okay, cool. Okay, so again, like I said, these are all gibberish, right? But basically what you want to hear or what you want to see is basically what I have said previously, right? The idea of linear algebra, you find it in engineering, you find it in physics, you find it in computer sciences, in machine learning, you're finding it there. It's helping with a lot of algorithms. In fact, pretty much all algorithms that you would want to build in machine learning. Linear algebra plays a role there, right? And yeah, we have this image that shows maybe some people are like, what the hell am I doing here, right? But just calm down, right? We'll take it step by step. Yep. Okay, so I think pretty much same thing that I have said everywhere, right? Computer graphics, machine learning, engineering, right? But more specifically, right? In computer science, when you're thinking of, for those of us who are into maybe 3D modeling, 2D modeling, right? What really goes on behind the box, right? When you're doing 3D modeling or 2D modeling, right? Sorry, give me one sec. Okay, so what happens behind the box, right? Is it that the computer just does some magical stuff and you somehow just find out that everything works, right? But the reality is that it's some core understanding of linear algebra that makes that happen, right? What about images and colors, right? How do you manipulate images and colors, right? Is it just some magical stuff that you take a picture now and you can make it black and white all of a sudden, right? What's really happening behind the box, right? We've spoken about machine learning, right? When you talk about engineering, you're thinking of load test, stress test, and the rest of it, right? Where does the idea of linear algebra, where does it come into play? In economics, right? Similar thing. Where does the idea of linear algebra come into play? Yep. So we'll take some specific examples, right? So your self-driving cars, right? So if you're familiar with linear algebra, right, you'd agree with me that or whether you're familiar with linear algebra or whether you're not familiar with linear algebra, right? If you have a self-driving car and this self-driving car is in some somewhere around Lagos, right? One question that I'll ask you is, how does the car know, even though I know there are no self-driving cars in Lagos though, but how does the car know where it is at a particular point in time, right? How does it know where it is in that particular space or in that particular map, right? Can anyone just maybe give me an idea of, or give me what he thinks as should be the probably reason why, or yeah, you can speak up. No, don't use the chat box. I like people speaking.
Latitude and longitude, right?
Okay. So okay, latitude, longitude. Okay, so but let's say that let's lower the idea of, just think of it on a flat, okay, take a look at this guy, this particular image here, right?
I think it is GPS.
That plane, that's why plane. So you can reference itself on that surface on the street.
Yeah. So pretty much there are a whole lot of coordinate things happening behind the scene, right? So not just to a car, right? Even to we humans, right? The place where you stand, right, is usually relative to something, right? So invariably meaning that you can kind of find your location. Maybe you could define your location as maybe I am 5 steps away from maybe the table or from the door, right? In the X direction, in the Y direction, something like that. So basically the whole idea of what I'm trying to say, it's not like I'm teaching you positioning and the rest of it. It's just more or less like telling you that the idea of linear algebra, it applies here, right? Finding out the position of something and how that particular thing travels to another location. Really, I don't know if you get my point. Relative to a base, some sort of basis that you must have defined, right? But this is how you will look at it from a physics, engineering kind of perspective, right? But it's, again, linear algebra is not limited to this, right? So let's go to something that some other people will relate with, right? So for those of us who are in banking or in insurance, right, let's take a look at this scenario here where you have some table, right? So in insurance, there's something called term life, whole life, and universal life. I don't think there's universal life in Nigeria, Dukor. And then you have age groups, right? And then you have some probability of mortality, and that's probability that people are going to die. And you want to kind of use this probability to know what's the payout, right? What the expected payout would be, right, for these different age groups, right? So in insurance, your premium, right, is based off your life expectancy. So actuarial scientists do a whole lot of computations, right, to pretty much calculate, right, the probability, calculate the premiums based on probability that these individuals would pay when they come to buy an insurance policy from them, or a life insurance policy from them, right? So, but now you are an actuarial scientist and you are presented with this data, your age group to the left and your probability to the right, and you want a situation where you want to multiply the probability of for age 20 to 23 by the difference for the term life. You want to multiply for that for term life, for whole life, for universal life. You want to do the same thing for 31 to 40 for term life here, where you're having 800, 600, and 300. You want to do that same computation for 41 to 50, where you're having 500, 700, and 400. So pretty much what I'm saying is you want to do a 0.004 times 500 and plus a 0.0045 times 700 plus a 0.0005 times 400. How do we kind of do this computation in such a way that it's not going to frustrate our minds as actuarial scientists? And for computer scientists, how do we do these computations in such a way that we are not having more than 5, 10 nested for loops, right? That can be very, very confusing and frustrating, right? So you see that this is kind of a different scenario where linear algebra comes into play. Okay, so off topic. And I said plenty things that maybe some people don't understand, some people don't understand, right? So let's go into something different. How many of you know this lady? You can unmute, please. Okay, what's her name?
Kwale.
Is that
Lady Kwale.
Yeah, Lady Kwale. So what's she known for? Where did you see her?
I think she's on Naira notes.
20 Naira note. 20 Naira note.
Yep. So she's on our 20 Naira notes. Okay. So now that we've taken a break, a chill, now let's go into some more serious stuff, but really interesting. So I'll start with vectors, right? So vectors really are they're mathematical objects that, as we might have learned in school, they have some length and then they have a direction, and they are usually represented as an arrow, really. A computer scientist would say a vector is just another list of numbers, right? So think of it as a number, some list of numbers in some numbers in a list, really. And why can't I click this thing? Right. So pretty much this is what you would see as a vector with an arrow at the top, right? And the square bracket just indicates it's kind of like a list of numbers, right? And what it pretty much means is that the 3 is saying that you're moving 3 units to the right and 4 units up. but it won't make sense until you look at it on a Cartesian plane, right? Plot. So what I mean is, when you look at this plot, right, what it's basically saying is that, what this vector is basically saying is that from your origin, 0, 0, right, if you move 3 steps to the right, which is invariably means your 3 is representing direction in the x-axis, right? And you move 4 steps to the top, right, which is 1, 2, 3, 4, right? The point you have here, or the arrow from here to here, which is typically 1D, right, is the vector. It's basically this vector that you see here, right? I'll pause in case anyone has any question.
I won't lie, I don't actually understand this in the way I should. So I don't know if you can do further explanation, please.
Okay, so okay, so you're familiar with graphs, right? X, Y graphs. You have your x-axis. So the horizontal, right, is your x-axis, and the vertical is your y-axis, right? And in this scenario, right, we've chosen our origin to be at point 0, right? So now, when we say 3 here, right, 3 is basically saying we want to move 3 steps or 3 units to the right, on the horizontal axis, which is your x. So invariably saying, the scaling here is by 2. So pretty much it's a 1 somewhere here, 2, and then 3 somewhere here, right? So if you trace that up, or if you just hold that point, right, or just to draw something like a dash line, something like that, and you count also from here, 1, 2, 3, 4, and you put some dash lines to this point, right? This point, the line from here to that point, is your vector. Does it make sense?
Yeah, I understand better now. I understand.
Okay, does anyone still have issues with what I have said? I think I may have to bring up my tab. I hope we can finish this lecture, because it's quite a lot. Does anyone have any other questions? Need me to go back? Okay, so yeah, so cool. And it turns out that there's something that there are row vectors and there are column vectors. So typically, right, your column vectors, as you'll see here, so column vectors are pretty much so first things first, vectors are one-dimensional. So what I mean by that is, it's either a 1 by something, right, or a something by 1. Okay, so Jack raised up his hand. You can ask. You have a question, right? Does Jack have a question? Okay, so I'm trying to bring up. Just give me 1 sec, please. Trying to bring up my tab so that I can make you all follow better. Just I'll just leave that. Okay, so as I was saying, So pretty much, if what I mean by a 1 by n vector, right? There is this notion of dimensions, kind of, right, in vectors and matrices and in algebra generally, where you want to know kind of the shape, really, of a. I'm sorry, I wrote matrix here. It's still a matrix, so vectors are kind of special matrix, but you want to know the shape of your vectors. Let's bring it to something that you can relate with, right? If I gave you look at this image we have at the top right corner. If I gave you this image, right, what would you say is the shape of this image, right? So the shape of the image is basically the number of rows by the number of columns. So in this case, can someone just tell me what's the shape of this table would be? Anyone?
Can you hear me?
Yes, I can hear you.
5 by 4. Am I right?
Exactly. So it's 5 by 4.
Okay.
So it's 5 by 4 because you have 5 rows, right? And then you have 4 columns. So similarly, when you take a look at what we have here, this particular vector v that we have here is pretty much a 2 by 1, right? Pretty much saying it's an n by 1. It's also saying that it is what? A column vector, right? In the same way, this is a 1 by 2 because you just have 1 row and 2 columns, right? So this is a 1 by 2. And anywhere you have a 1 by n vector or special matrix, right? It is it's really a row vector, right? Okay, that said, one other thing I would like you to know is that in the space of linear algebra, right? The idea of column vectors and the idea of row vectors kind of differ in the sense that column vectors kind of mean something on the plot, right? So that's why we are plotting this vector on this plot, on this Cartesian, right? A row vector is pretty much not something you can put, I mean, you can put it on a plot, but mathematically, it's more of, it's just for mathematical operations, really. So if you are going to represent a vector, you will want to use a column vector, not a row vector. Okay. And
Please, Kenny.
Yep.
Please, can you go back to the last slide, please?
Okay.
Okay, now how will someone know which is a row vector, and which is a column vector?
So just like I said, right, where you have an n by 1, this is not x, sorry, this is not like a x alphabet, it's like multiplication, not this. So it's an n by 1. So any dimension n by 1 is basically a column vector. Any dimension 1 by n is a row vector. So by looking at it, you have this, for this v, right, you have 2 columns, two rows and 1 column, right? You know, here we had said it's a 5 by 4, right? Here,
Okay.
it's basically going to be a 2 by 1. And because it's a 2 by 1, right, it's invariably column vector. I don't know if
like,
yeah.
see, like I am beginning to understand you now. Now, this vector that we plot, the vector 3 and 4, how then do you transpose it to be 1 by 2 or 2 by 1? I don't know. 2 by 1. How do you do, like the 3 and 4, the one we plot, the vector plot that is on the slide now?
Mm-hmm.
Okay,
So
I'm sorry. I think from my understanding, 3 by 4. If you look at it like maybe the arrangement 3 and 4, it's on a column, right? Then that's yes, it's on one column. Then the 3 is on a particular row, the 4 is on another row. So that is a 2 by 1. That is 2 rows and 1 column, right? I think that's the explanation. I don't know if I'm right.
Yeah, you're. I don't know if it clarifies it. Or do you need me to go over it again? Hello?
Yeah, I'm with you. I'm with you, sir.
No, not sir, please. Just Kenechi.
No, I'm with you. You're my teacher. So me call you sir. There's nothing wrong there. Okay, I actually understand the explanation my fellow actually did there. I just took my eyes up to look at the diagram up there. And I think I'm beginning to make much sense of it.
Okay, makes sense.
But it's okay. Much more later, I might go through the slide again. Maybe.
Okay. No, it will make sense. Let's move on. Okay. Okay, so some English stuff, right? So when we are talking about vectors really, right? Or we are talking about linear algebra really, right? You know, I had said something about dimensions referring to the coordinates needed to specify. So basically dimensions are the coordinates needed to specify a point, right? So what I mean by that, I really need to write. I really need to write. Just give me 1 second, please. I need to connect to this thing. It's a bit hard for me to explain. Okay. Okay, sorry. 1 second. Okay. Yeah. Okay, yeah. So I think it worked. Oh, okay. This. Can you hear me? Can you hear me?
Yes.
Yes.
Yes, we can.
Okay.
Yes, we can hear you.
Yeah. Just trying to figure out this stuff. Yep.
Someone is writing on your screen. I don't know who is that person.
No, this time around it's me.
Okay.
Okay. Okay, so so basically what I'm trying to say is this. Like a dimension refers to the number of coordinates, right? So when I said dimensions refer to the number of coordinates. So take for instance, we have we have, why does this? So we have this, right? Y, and we have X. Take for instance, the number of coordinates we have here, right? It's 2. We have the X and Y coordinates. In this situation, the number of dimensions is it's pretty much 2, right? We could also have something which you're all familiar with, and which is even something that everyone should be familiar, should know, right? I mean, our world is kind of considered as 3D, is something like this. Yeah. X, Y, Z. So if we have this, we are saying that we have, it's 3D, right? So let's go back to the case of 2D, right? Sorry. Jeez, man. So let's go back to the case of 2D, where we just similar to what we have here. Come in, please. It's not the best. Okay. Let's go back to the case of 2D that I had drawn earlier, right? So where we have something like this. Now, the set of points that we have that describes that is on this 2D coordinate, right? I mean, pretty much the coordinates kind of define positions, right, on this 2D, on this plane, pretty much, right? So let's say, for instance, you want to, just like we had seen earlier, in a 2D plot, let's say, think of it as your room currently, divide your room into, think of it as your room, right? And then you divide your room into lines, right? Equal lines, something like this. If you want to define a position in your room based on the fact that you are considering it as a 2D plane, right? Or a two-dimensional world or something like that. A position on your room can be somewhere here, right? Based on, with reference to some reference point, right? Or some basis, which we can say here. Now, if we say this place is 0, 0, right? And we say each step or each unit is 1, right? Then how can we define this point here on this Cartesian? It's pretty much something like this is 1, this is 2, this is 3, right? And this is 1, and this is 2, really, right? So this is 1, 2, 3, and this is 1, 2, 3, and this is 1, 2, right? It invariably means if you trace this guy up, let me use a different color. If you trace this guy up, and you trace this guy to the right, the intersection, which is here, is pretty much the position of whatever object in this plane or in this dimension, right? So that's basically what all this is saying here, right? So you could have dimensions in 2D, right? And if think of your triangle. Your triangles are 2D because you're basically defining points, right, on a 2D plane or on a two-dimensional world, something like that, right? Your square is 2D, right? Because it's also defined on a 2D dimensional world, right? However, if we leave 2D and go to 3D, this is something we see more often in our day-to-day lives, right? Things become volumetric in this situation. So so we have something in 3D, right? So let's say this is your X, this is your Y, this is your Z, right? If you want to represent something in this dimension, right? Think of something like your cube. Yep, because your cube has a volume. Right, and each of the different edges in your cube can be defined by a position on your X, Y, and Z um, 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 X, Y, and Z coordinates frame, right? So quick question before we move ahead. If a vector, right, identified on a 2D plane, right, is given by, I think we had said 3 and 2, right? Let's say there is a third coordinate, right? Something. How would it, what would it look like? Or how would we be able to visualize, or how would we be able to visualize the third coordinate, right? That, or a vector that has a third coordinate, or how would we write it really?
So it will be 3, 2, and another point under. So it will just be like a 3 by 1 matrix.
Exactly. So basically, this is what is going to be, where this will define a point on the X, right? This will define a point on the Y. This will define a point on your Z. So by the time you trace it somewhere here, you all meet at some point here, somewhere here, something like this, right? I don't know if it makes sense. Does it make sense? And that's pretty much the reason why I said we have to do practical. If not, it's just going to be all gibberish. Right, okay. Let's move ahead. So there's also 4D, but 4D we can't visualize, right? So I won't even say much about that. Even I myself, I have not seen it. That's maybe something in space or something. Maybe some people have seen it. So, but it doesn't mean that in practice, you are not going to see things like that. You're going to see very, very high dimensional matrices or vectors that you'll have to operate on. So in as much as you can't visualize them, right? Take, for instance, machine learning, right? In as much as you can't visualize them, you should be able to make computations, do computations. Okay, so for some reasons, is it that the technology is so bad today or what? Okay, so it's moving now. Okay, so so vectors have operations, right? Similar to think about your mathematics. 2 plus 1 is the same thing as 1 plus 2, right? 2 times 1 is the same thing as 1 times 2. You know, we have all these rules in mathematics, right? That makes mathematics work, right? So it turns out that vectors also have similar rules that apply to them when you are using them in practice. So take, for instance, I give you a list of numbers, right? So when I say I give you a list of numbers, I mean, I give you 1, 2, 3, right? And then I give you 3, 4, 5, right? What does it mean when I say this matrix plus this matrix, right? What does it mean when I say, I did this thing again. What does it mean when I change it and I say this matrix minus this matrix, right? Minus, right? What does it mean when I say some matrix A, B, C, or right, multiplied by some number 2? Do you get? What does all these different things mean, right? So we'll take a look at the different operations that exist in vectors. And then once we are done with that, what we'll do is we'll take a small play break where you all will go to Colab and try these things out. So again, please don't be discouraged, right? That you don't really understand these things. It's going to make sense. And even if it doesn't make sense now, as you keep encountering these things over and over again, it will make more sense, really, right? Okay, so so one of the rule is vector additions and vector and dot products are commutative, right? Commutative. So what it's basically saying is, if you have some vector A, right? So when I say vector A, I mean vector 1, 2, 3 is equals to A, right? And you have some vector B, right? Vector 3, 4, 5, right? We are now saying that if you add A plus B, right, it is the same thing as saying B plus A, just like you have in your math. So there's nothing, there's no magic, there's no funny thing happening behind the scene. It's just the same thing, right? The same thing, similarly, when you say dot products. So dot products, we'll go into details of how dot product works, but similarly in vectors, when you say a vector A times a vector B, right? Or dot product B, right? Like I would prefer to say, so there's no confusion, right? This action is also commutative, right? In addition, vector addition is associative in the sense that similar to your mathematics where you have A plus into bracket B plus C, or 2 plus into bracket 3 plus 5, right? It's the same thing as 2 into bracket 2 plus 3 close bracket plus 5, right? It's pretty much the same thing. So what you're saying here is that just like I had said, written above here, right? If you add your A, if we have like an extra vector, say 6, 7, 8, right? When we say A plus into B plus C, it's the same thing as saying A plus B plus C, just like we have in math. 2 plus 3 plus 4 is the same thing as 2 plus 3 plus 4, right? Makes sense. Makes sense. I'm not even seeing the chat. Let me take a look at the chat. Yep. Okay. Okay, cool. Yep. So, but does this make sense? I'm pausing to get questions first before I move on.
I think if I'm understanding this thing properly, it's actually making sense, just like a simple math. We all
Yeah, exactly. Cool. So like I said, it's very simple, and I just want you guys to kind of conceptualize it, right? You might just end up finding out that what you'll keep on doing is more of matrix multiplications, dot products, cross multiplications later on, and you're pretty much going to be using libraries to do that. But just understanding this would help you debug. Trust me when I say it's frustrating when you have to debug errors that have to do with dimensions, right? Or shapes, you get, as you would also hear, right? Trust me, you don't want to have that issue. And if you kind of understand this well enough, right, the probability that you spend a lot of time debugging errors is going to be very minimal, right? Yep. Okay, so now let's go. I didn't arrange this slide thing very well. I wanted it to be very interactive, that everybody will be very happy. Okay, so we'll come to that. Okay, so let's take a look at vector addition, right? So very, very simple, right? If you have a vector 3, 4, and you're adding it to a vector 1, 2, is the same thing as taking the element 3, right, here, adding it to this guy here, and taking the element 4 and adding it to this guy here. That gives you 4, 6. So a question of pop quiz for you guys, right? What if I add a third dimension, right? 1, 2, 1. What would be the output?
I think it's the same thing. 3
4,
plus
6, 2.
1. 3 plus
4,
1.
6, 2.
Yeah, 4, 6, 2.
Cool, makes sense. Right. So you guys see that it's not hard, right? Let me clean what is this guy. Let me clean this guy. So now, what about the difference? Someone explain it.
3 minus 1 is 2. 4 minus 2 is 2. It's understandable.
Okay, cool. Makes sense. So what about this?
One is dot multiplying dot product of 2 and matrix 3 and 4. 2, 3, 6, 2, 4.
It's just scalar multiplication, a scalar multiplying through a vector. So it will like do a broadcasting to it. So it's like 2 multiplying through the vector.
Okay, makes sense. So you guys see that it's not magic, right? So but let me ask one question, right? This 2. So basically we said scalar multiplication. What is this 2 doing conceptually? Try to imagine. So you see, conceptually, we had drawn like one arrow facing to the right, to the top, something like that. Conceptually, what is this number letter? I will just start with this number 2. What do you think number 2 is doing to this vector 3, 4, right? So think of it as you said something. Let me draw it, right? Let me draw it. So we are saying that this is 2, this is 3, this is 4, this is 5, this is 6, right? And this is 1, 2, 3, 4, and we have 8 somewhere here, right? So if we say we initially had a vector 3, 4 somewhere here, so we can say it is this, right? And then you multiplied it by 2, and it becomes a vector 6, 8 somewhere here, right? What would you say? So think of it as this is let's say 3, 4 is say U. So if this is U, right, it invariably means this guy is 2U. So what would you say 2 is doing?
2 multiplies the effect of that vector. So, for example, if you have a weight, right? If you have a force that is applied on a wall, like if you punch a wall now, right? A particular spot on the wall, that is what that vector is 3 or 4. Then the 2 will be like a multiplier that says you are increasing the effect of that force on that particular spot. So here now, if the 3, 4 were to be like acceleration, then the 2 will be like you are multiplying the acceleration by 2 in that particular direction.
You see, and that's you see, this is why linear algebra it's very, very interesting. So if you listen to him carefully, he spoke about it from the point of physics, where you're thinking of something moving in a direction, right? And then you increase the effect of that thing moving in that specific direction. Now, if you look at the chart, right, someone is giving a different perspective and saying there is a position that the vector u, right, signifies a position in a space, right, and then multiplying 2 by that position, right, it invariably means you are moving, kind of changing the position or something like that, right, or kind of increasing the length of that particular vector in that particular direction, something like that, right? So you see someone is looking at it from the point of, oh, something is moving with some velocity, and then you increase the velocity in that specific direction. Someone is looking at it in terms of maybe positioning, right? So you see that you can look at it in different ways, even in economics, right? Or in actuarial science, right? And where you say you're applying some differential value to say to a premium. What is that differential value? Take for instance, there's a change in the economy, right? That differential value is acting on what you have, which you can represent as a vector, right? And really the idea is that number 2 is pretty much scaling the vector, right? That's the general word you want to use, be it in physics, be it in computer science, be it anywhere. Pretty much the value 2 is scaling the vector, and that's because 2 itself, it's a scalar, right? So where you have just a number, right? Just 6 is a scalar, 7 is a scalar, really, right? Yep. So that's that. So let's move on. Give me 1 sec, because time is really, why is the time short? Yeah, so this is basically what I have said. So just a quick quiz kind of thing. So I want you guys to go to Colab, right? It's very easy. Please, everyone go to Colab. If you're on your PC. And I would want someone to share his screen. It's not going to be from my screen. Someone should volunteer to share his screen. So we are going to do this for just 5 minutes.
Let me share.
Okay.
I think there are some settings you have to do to allow me share.
Oh, wow. Okay, try to share again. So please don't just look at him, do it on your own end also. That's why the notebook is there. If you need me to paste the notebook on the chat, try to share again, please. If you need me to paste the notebook on the chat,
you have to make me a co-host so that I'll be able to. I can't. Okay, I can do now. Hold on. I can do it.
Okay.
Yeah.
Okay, I'll share the link. Give me 1 sec.
You can see my screen now, right?
Yes.
Okay. I've run the first cell.
Okay, no. So the idea is that I want you to explain what you are doing. So I've put the link on the chat, right? So you can check the link on the chat. Okay, so go on.
Okay, this is a plot, just like my plot.
No. Don't explain. Just run.
Okay.
This particular, yeah.
Okay. I've run it.
So we can just run this. These are just helper functions. Okay, so now this is where we are, right? So, no, creating a vector. So basically, one very popular tool that is used to manipulate vectors, matrices, and tensors, as you'll also hear, right, is NumPy. NumPy in Python. It's the most popular tool, right? You have some other tools in MATLAB and the rest of it, but we'll stick to NumPy in Python, right? So now, when you're going to create a row vector, pretty much this is what you run. So you're pretty much putting a list of numbers, right? As you would have in Python. I assume everyone is familiar with Python. You're basically passing it into a function in NumPy that is numpy.array. And when you pass that and save whatever the output is in a variable, the output you have is a row vector, right? However, if you want to create a column vector, it's a different approach. You kind of put it as a list of lists, right? So you're having a list, and each value within the list is also within a list, as you'd also see in the code. So run it, right?
Yeah, this is a row vector and a column vector. I understand.
Does it make sense?
It makes
right?
sense now. It makes sense.
Okay, so cool. Now I kind of did something here to show you that in NumPy, right? Sorry, can you change V2 to a column vector?
Okay.
So everyone change V2 to a column vector. No, change V2.
Okay.
No,
Okay.
the variable V2, reconstruct it as a column vector. Nope, reconstruct V2 as a column vector.
Hold on,
So,
let me go there back. Where is the
okay.
V2? Okay.
So you have V2, yeah. Or V1, anyone.
I can
Nope.
do like this.
Nope. So check
do like
it. Let's take a look at
like
it.
you have already created a variable here, called vector.
Oh, okay,
like-
okay, that's fine. That's fine.
Yeah.
Cool. Yeah, I didn't figure that's what you wanted to do.
Okay. It's cool now.
Yep. So run it. Let's
Run
see.
it again.
Right. So pretty much you see that when you're plotting it, right? So mathematically, well, it's not the same, but when you're plotting it, it's basically going to give you the same plot, right? So you see that the two are overlapping on themselves, right? That's why you don't see your V2, your V1, right? Which has the red color, but you see some traces of red somewhere around it. So what I want you guys to do now in the next 1 minute is play around the values there, right? Make it change the values, see how it changes around this this plot, and just kind of conceptualize it. Or no, we have some other things to do. So scroll down. Sorry. I think the next bit we want to see is this, right? So vector additions. So just like I had told you before, right? Vector additions are actually very also simple. They're also very simple. So it's as good as saying your V1 plus your V2, right? So you can run the code and see that whatever you have as V1, right, plus V2, as you would calculate with your hand, is the same thing as you would have here, right? So if you run it again, run the next one. So this is pretty much a plot that kind of describes what is happening when you do a V1 plus a V2, right? Which I'll explain. Just keep your screen on that, please. So what is happening here is this, conceptually, right? You can take note of this, not necessary, you could ignore it, but what is happening basically is this. You have some vector, say they call this your vector U, right? And you have this, call it some vector V, right? So take, for instance, you move 2 steps, right? This is 1, 2 to the right, and 1 step to the top to create this vector, right? And then you move 1 step to the right, just 1 step upwards, right? And you remain on the x-axis to create this vector U. Yep. Now, if you add these 2 vectors, it's the same thing as moving. So if you take this guy that is red, really, right, and move it up such that, think of it as you move it up to this direction, right? It's the same thing as moving from U to the top tip of U and from the tail of V to the tip of V. So think of it as a summation, right, or a resultant summation of U plus V. So it's more or less like if you were going to travel from U, from the tail of U to the tip of U, And from the tip of U to from the tail of V, which is the tip of U, to the tip of V, right? The summation of that whole travel, right, is what you have here, right? So this is your summation. So invariably saying that if I give you on this plot, right, think of it now. Let's say we consider something different. And I want everyone to take a look at the screen and try to figure it out. If I give you a vector, let me use a different color. I'll use this color. If I give you a vector, where is it? I can't write again. Okay, some vector here, right? Notice that it is this vector up here is 0, 4, right? Or think of it as, no, I don't want you guys to know what it is. And then I give you another vector, right? Defined by this. Looking at this plot, what would you say is the sum? Try.
What's the unit you're using to measure, please? The measuring unit.
So this is 2, 4. So this is your 1.
Okay.
Right, and this is your 1, 2, 3, 4.
That means the vector with the red arrow will be 2, 2 now. Am I right? Yeah.
2, 4.
2, 4.
No, 2, 2, 2.
2, 2, 2, 2.
But what's the sum? Irrespective, looking at it, the two vectors, what is the sum of the vectors?
I think it would be 4, 6.
4, 2. No, it should be 4, 2.
Someone said 4, 6. Someone said 4, 2.
So that would be 4, 6. No, I mean the other one.
Okay.
The red should be the extended one should be 4, 2. So if you add them, 4, 6.
4, 6, cool. So if you take this guy, this arrow, this one here, if you move it up to this place, it's going to be something like this. All right? Somewhere here. So it invariably means the sum is a vector that is somewhere like this, right? And this point here is your 6. This is your 4. So I mean x is 6. Your horizontal is 4. Your vertical is 6. So invariably meaning that you can basically just look at your diagram and know what it is, which is not what you'll do all the time, really. Please, right? It's just so that you kind of understand the concept of what is happening when you add, when you subtract, right? When you're subtracting, basically, right? Whatever is going to be subtracted, right? So let's say you're subtracting this vector from this vector, right? The subtraction from this vector is more or less like you're taking this guy to the negative, right? Maybe just kind of putting it in this direction here, right? And then you're now using, based on this new position, we are moving it up somewhere here, right? And then whatever the vector is here is your summation, right? So some fun stuff, but let's continue with the code. Cool. Let me clean all these things I said. Are there any questions, please? Please ask questions.
Sir, I didn't get this last part where you drew something like a triangle. What did you call it?
The subtraction bit.
Subtraction bit.
Is it where I said subtraction, or is it the last thing I did?
The last thing you drew, yeah,
okay.
like a big triangle to connect.
Okay, so what I was saying is, that if you have some vector 2, 3, and you have some vector 3, 4, right? when you add, we already saw what addition is, really, right?
Yeah.
But when you subtract, right? When you subtract, think of it as you are doing 2, 3 plus minus 3 minus 4. So it invariably means if this 3, 4 was maybe this guy, this vector here, this red one here, right? Minus 3 minus 4 is a different vector. In the opposite direction.
Okay, I think I get it now.
Right, cool. So if you're now going to find the whole, just the same exact thing that we've been doing before, right? Okay. Okay, so let's continue running. Good.
Please, excuse me, please. I have a question.
Yeah.
Please, how did you get 4 in the blue vector? I know how you get able to get 0 and 1, but I don't know how you got 4.
Okay. Okay, you mean this? So pretty much it's just addition, right? Sorry, which 4 are you talking about?
The blue vector of 0, 1, and 4. I know how you got 0, 1. Now I got 4.
Yes. So you have 2 vectors. You want to add them together. So imagine that your vector 1 and your vector 2 are given. You want to add the 2 of them together. So your vector 2, 1, 3 is given to you. Your vector 0, 1, 4 is given to you, right? Now, what is the summation of vector 1 and vector 2? It's going to give you some vector 3, which is 2, 2, 7, right? So basically, what we basically did is we picked that vector 1, vector 2, and then we plotted it.
No, I'm talking about in the plots, how they got 4 in the plots.
Oh, okay.
So you already represented it. The blue vector is represented in the graph. How 4 was gotten in the plot?
Oh, okay. Yeah. So okay, let's scroll down.
Down or up?
So I understand what she's saying. So if you scroll, no, keep on going, right? So pretty much it's 3D, right? And that's the point I was getting to, right? So if you check the first one, she was already confused. She didn't know how she would see it's like the 3 dimensions, like kind of visualize it, right? Turns out that on this also, it still doesn't make any sense. Visualizing it doesn't make any sense. It's basically the same as the one above. So scroll down again. Why didn't I put this? Sorry, can you copy the last, no, sorry, the where you have cross product? No, scroll down, sorry. No, not up.
The cross
so
product.
Yeah, so you see where you have the plot. Can you copy it, please?
Okay,
Right.
you copy the plot.
Yes, copy everything. Create a new code block just beneath the plots that you just had.
Like this one?
Oh. Yeah, exactly. Create a new code block just beneath this guy.
Okay.
Yeah, paste it there.
Okay.
And then plot it, let's see.
I should run it?
Yes. I thought I put this here. Interesting.
Still running.
Yeah. So here you can kind of pan. So if you drag around this guy, you'll see that. Sorry, can you drag? No, not zoom. Like use your mouse to click on the screen and move it around. Right. So this is what you want to see, right? So your X is on some point, is pointing to some X, is referencing some point X in the X-axis. Your Y is referencing some point Y in the Y-axis. Your Z is referencing some point Z in the Z-axis, right? And that's how you get your point. I don't know if it makes sense now. right? So that's why you'd see it's kind of, so you see take it to the tip of one of them, take it to the tip of, yeah. So you see your vectors, right? You see the positions, take it to the tip of the green guy, right? Take it to the tip of the blue guy. So you see that you're able to represent it better with something that you can actually move around. This is just to make it more visually appealing, right? So if it is already getting confusing to visualize things in 2D on your screen, think about what it will look like in 4D, in 5D, that we can't even visualize it, right? I don't know if it makes sense.
Yes, thank you.
Yep, cool. I actually missed that.
Okay. Please, Kenny.
Yeah.
Okay, the green plot is a summation of the blue and the red. Am I right?
Yes.
Okay.
Okay, so there are some to-dos, right, which I would leave you guys to do. And I want us to skip to, and then scaling. I already described what scaling is going to be like. So I'll leave you guys to do that on your own because of time, so that we can move on to some other stuff, right? So I think I'll share my screen again. And then there is cross product, which I will describe. So cross product, someone asked the question about, okay, before we get there, let's just go back to the slides. I'll be sharing now. Give me 1 second. Man, we have a lot to cover and we are just here. Yep, let's see. So I guess everyone understood what kind of happened back there, yeah? And we are done with this stuff, right? So it turns out that based off what you've seen, right, it's it invariably means everything that you see here makes more sense now, right? So if you're doing a vector addition, right, and you have some vector in this direction, some vector in this direction, the summation is just something, it's like a resultant, really. And when you're scaling, as you would see when you try it out on your own, right, if you have some vector v and you multiply it by 2, it's going to give you a vector 2v. If you have some vector w and you multiply it by 2, it's going to give you some vector 2w, right? Now, who can tell me what is happening in the third plot, on the third stuff to the right? Anyone? Maybe there will be a prize, I don't know. Take a look at it. Tell me what's happening.
I think it's cross or something. Sorry.
Take a close look at it. Anyone? Is someone trying to speak?
Is it both scaling and addition?
Exactly. So pretty much you're scaling your v, your vector v, by 2, and then you're adding it by vector w, right? That's basically what's happening there. And that's why you'd see you have 2v plus w, right? So you're doing a scaling, and then you're doing scaling of one of the vectors, and then you're adding, right? Cool. So, I mean, we've done all this we've done all this, so, and there's even a typo there, so we can move on. That was just pretty much 3D, which you guys have done there. So there is this notion of dot products and someone that which is and cross products, which is matrix multiplication, like someone said. Right. So the idea of dot product is this, and please, this dot product is very important when you're dealing with matrix vectors, and even when you start dealing with matrices, because this is the bit that I want everyone to really pay attention to, because you'll see it everywhere you go. Right. You need to, when I was talking about dealing with dimensions and if you're going to have errors, and if you don't understand this bit, it's going to give you issues, right? It's because maybe few people don't really understand or didn't do the due diligence to know what happens here. So let's say you have dot product is basically gives you dot product between the two vectors, pretty much gives you a scalar value, right? But it's not a case where you're just saying 1 times 3 and then you're doing 2 times 4. All right. If you do that, that's called something else. It's called element-wise multiplication. But that's not what we want to do here. Dot product is something different and something I would say very powerful, right? In words, it's the sum of products of corresponding entries of two vectors, right? And if you're going to put it out on paper, it's going to be 1 times 3 plus 2 times 4, right? Which doesn't really make any sense conceptually here, right? But before we go to what makes sense, there are some things we need to know first, right? And that's the idea of transpose, right? So transpose, as you'll see, right? So if you take a look here, anywhere you see in linear algebra matrices, anywhere you see, like say, an A with a T, you're basically trying to say a transpose of some matrix or some vector A, right? Sorry, 1 sec. I don't know why my Zoom has kicked me out on the other device, on my second device. Just 1 sec, please, so that I can write. Hold on, please. Okay. But it says I'm in the meeting now.
You are here now. We can hear you.
No. Like I'm on my second device. It says I'm not there, which is weird. Give me 1 sec. Yep, so I'm back. Okay, so where you see this T, right? Just like I was saying, it just means transpose, right? But what really is transpose? Think of it that you have in the context of vectors, right? Think of it that you have some vector 1, 2, right? The transpose of this vector 1, 2 gives you like a row vector. This is a column vector, right? We all agree the column vector. And the shape of this vector is 2 by 1. We all agree with this, yeah? If you're going to do the transpose of this vector, right, it's going to be a 1, 2, right? Which is now a 1 by 2. So that we don't get confused, I'll do this again. We have a vector 7, 9. So what's the shape of this vector? Anyone? Anyone?
2 by 1.
Yeah, 2 by 1. So when we transpose this, see this is a vector B, right? When we find the transpose, so B hyphen T, what will the vector become?
1 by 2.
But what will be like? It's going to be something. Is it something like this? Is it this? Is it this? Is this it? And no one is answering you. No, okay. So yes, it's not, right? It's really it's really a 7 by 9. So think of it like you're rotating this guy, right? Turning it. You get so yeah, that's pretty much what the transpose is. So you can take a look at what it is defined as more formally, where you're having an A matrix, an IJ, blah 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 blah. That's not really important to us, but yeah, it's something worth looking at. So it turns out now that I mean, this is what we just looked at, right? So similarly, when you have let's say we have this now, right? 3, if you do the transpose of this, right, it gives you a 1, 2, 3, right? You can ignore the one that's this. We'll take a look at it later, or you could look at it now, right? So let's say you have it in more numbers, something like 1, 2, 3, 4, 5, 6, right? The transpose is pretty much you saying, you want to take this guy. Think of this guy as a vector. Think of this guy as a vector. Think of this guy as a vector. When you turn this guy, it becomes a 1, 4. Now, on the next line, you turn this guy, it becomes a 2, 5. You turn this next one, it becomes a 3, 6. Right? And we're going to use this in the next, in some few minutes to come. Does it make sense? Does it make sense?
Please, I don't really understand what you just did. I don't know if you can actually explain it again, please.
Okay, sure. So, so think of it that you have, we are not having vectors now. Think of it that you just have something, some numbers, because reality to make sense later. I'm bringing it up now so that when that time comes and I ask the question, everyone will say, yes, I understand what is happening here, right? So think of it that you have this guy, right? Sorry. So you have this guy, 1, 2, 5, right? 3, 6, right? Now, this is more two-dimensional than one-dimensional, right? It is not a vector. Just forget about what it is now, right? Now, if you're going to do a transpose of this particular guy, right, it's going to be something like, imagine this guy is a vector. Imagine this guy is a vector. Imagine this guy is a vector. And they have been put side by side. Yep. Now, if I do a transpose of this guy, based off what you know now as transpose for vectors, it is going to be a 1, 4. Agreed?
Yeah,
right?
yeah.
Cool.
I understand now. I understand exactly what you did now.
Okay, so if 2, 5, and then you have a 3, 6. Right, so basically giving you a 1, 4, 2, 5, 3, 6. Cool. Okay. So let's go on. Right, so this is transpose. Now, moving ahead. We are now going to go back to the dot product we had done before. That didn't make any sense. So we have some vector 1, 2, and some vector 3, 4, right? It turns out that if we are going to do a dot product of some vector A by some vector B, it will be such that you're having, you're pretty much having a row vector multiplying a column vector. I don't know if it makes sense. Right? Such that when you have your row vector, when you turn one to become a row vector using transpose, right? You know, you now have an A transpose, which is now equals to 1, 2, right? If you do the dot product with this guy, invariably meaning it's kind of, forget the word, right? Well, leave that. You have a dot product with this guy, right? It is basically you saying, think of it as conceptually, think of it as this is your X, this is your Y kind of thing, right? And this is your X, this is your Y kind of thing. Just think of it like this conceptually, right? Initially, you had it as, okay. So initially you had it as, I'll clean this, give me one sec. Initially you had it as, sorry, give me one sec. I'm trying to clean this thing off. So yep. So initially you had it as this guy, right? Then you think of it as this was X, Y, X, Y, right? Now you want X to operate on X and Y to operate on Y, and then you do the sum. So if you do a transpose, right, 2, you can only use a transpose to act on the other guy, right, which is now going to be this guy, such that your 1 is going to, which is pretty much your XY, right? Your 1 is going to multiply 3, right? So 1 times 3 plus, because you're still in the same row, right? Because you're still in the same row, your 2 is going to multiply 4, right? This is what your dot product is. So think of it as your row multiplied by the column. I don't know if it makes sense.
Yeah, this whole vector thing is actually very simple to understand, but the name alone make it look so complicated, like make it look like it's the complex stuff.
Yeah, it's really not. Does it make sense? Does anyone have any question? Okay, cool. So this is what your dot product is. And trust me when I say, if you understand what just happened now, right, it's basically what you're going to see over and over again, right? The idea is you want this, this whatever you have here as X, right, to multiply what you have as X here, probably this guy, because they are pretty much in the same dimension kind of thing. You're kind of doing some sort of transformation, right? So this guy is multiplying this guy, and this guy is multiplying this guy, and then you're adding them together because it's just pretty much the same row acting on a column, right? So that's your dot product. So the reason why it was, I mean, it's easy to say, why did we need to do the transpose, right? The reality is that if you're doing dot products, you just have to do the transpose. If not, your computer won't even understand what you're trying to say, right? And the idea of dot products, multiplying rows by columns, right? The idea of multiplying rows by columns, one very good thing it does is that it alleviates the stress of, let's say, for those who are very good at programming, for loops. So take, for instance, I said, I wanted to do this with, sorry, someone said, can we multiply 3 by 1? Sorry, can you multiply 3 by 1 with a 1 by 3. Yeah, you can. But what you would have, if you construct it, right? So you have 3. Say A, B, C, right? And you have a 1 by 3. A, B, C. So pretty much what you're doing is this times this plus this times this plus this times this. It still gives you a scalar. Right? So okay, let's even say let's even make it even clearer. Right? C, D, E, F, right? So what you are going to have, right, is A times B, A times D, right, plus B times E plus C times F, right? Now, if you take this guy to the other side, right, it's still your D times A plus E times B plus F times C. I don't know if it makes sense. So I'm responding to the question on the chat. Right. So pretty much one thing that you should pay attention is this. Irrespective of the dimension, right? Irrespective of the dimension, there is a rule that your M by N, you can only do a dot product on M by N with in fact, scrap this. This is for matrices, not for vectors, but I'll just leave that. So when we get to matrices, I'll say that because it doesn't apply to vectors. But I don't know, do you get what I was trying to describe? I don't know who asked the question. Akoridi. Yeah, I can hear you.
Hello, sir.
Yes,
Sorry,
thank
I
you.
like to like invariably. Hello, sir. My name is
Yeah.
Christopher. I like to like invariably. Does it mean at every point dot product simply means the for an A and B? Oh, sorry. Hello, am I audible?
Yeah, I can hear you now.
Okay, for an A and B, what to transpose? Is it like a law that it is A transpose B? You cannot transpose B.
So you can transpose.
Fine, that's the way to for dot product. Now A is what you transpose to multiply.
So
you transpose.
Okay. So for vectors, right? Vectors like 1 by n, n by 1, irrespective, right? You can transpose anyone. So if you're having you can transpose anything you want to transpose, really. But the idea is this, right? You shouldn't have 2 column vectors. You programmatically, right? If you try to do a dot product of 2 column vectors, you're going to probably get an error, right? So it's usually like a column vector multiplied by a row vector multiplied by a column vector, right? So you do your row and column. But we'll see this. You'll see more sense in it when we go to matrices, right? So just let's just have kind of put that somewhere in our mind somewhere. Right? And I think I get what the question you're asking, right? So it's more or less like, so thinking about it now, it should work, right? So 3 by 1 is, and 3, no, it doesn't work, 3 by 1. So what you're trying to say is 3 by 1 multiplied by, so what you just, or what would bring more clarity, right? Think of it as you have a 3 by 1 multiplying a 3 by 1. all right? If you want to multiply a 3 by 1 by a 3 by 1, right? Really, you want to have the elements in these positions to be the same, right? So one has to change. You can make it this guy so that it becomes a 1 by 3 acting on a 3 by 1, right? Or you change this guy. So now say it's now a 3 by 1 acting on a 1 by 3. Makes sense, yeah? Okay, so let's move on. Hopefully the remaining part of this lecture is going to be fast. How many minutes do I have? Sorry. How many minutes more?
3 minutes.
Hey, how many more minutes can I take as extra time?
We can finish the class. We can actually pass a vote. You can put a poll on the chat box, whichever time you want to use. We can vote on it.
Okay, please vote. If you say I should go, I'll go and come back later. Anything you see. But while the vote is going on, right, I'll just continue. Okay. So yeah, that's vectors. And there's also cross product, right? Cross product is different from dot product, right? But the idea of cross product, I'm not going to go into much of the details because of time, but think of it as when you do a dot product, it gives you a line that is perpendicular, and it only happens in 3 coordinates, right? So think of it that you have a line. Think of it that you have a line x and y, right? So this is x, y, and you want to this is x, y, right? And you want to find a line that is perpendicular to these 2 lines, right? In some space, right? In a 3D space, right? Think of it as so this sorry, let me correct this. You are in some 3D space, right? This is Z, X, Y, right? You have some.
Kenny, sorry, please. Do we have lab session today?
Yes, you do.
You know, we actually have to go for the lab session. So I would say maybe you create a poll on the Discord channel. If then you fix a time that is favorable to you, you will vote on it during the weekdays. We'll vote on it, then the majority of it, the majority vote cast, then you choose from there. I think that will be better now.
Okay, so let me round up vectors in 2-3 minutes. No, or give me 10 minutes. Is 10 minutes fine? Okay, I'll guess yeah. Someone says yes, so continue. Okay. So so you have some vector, like you have some space, and then you have some vector in this space, say U, and you have some vector in this space, say V, right? What your cross product does is that it gives you a line that is perpendicular to these 2 vectors, exactly perpendicular, right? Say Q, right? That's what it does. So it might not be too relevant for you guys now, but as you go on, you begin to find that it's really like a thing, like a good gadget when you're probably building models and you want to find a kind of orthogonality kind of thing on a 3D dimension, right? And again, it's very simple, right? It's a very simple formula. Yeah. So cross product is basically, think of it that if you want to find the x dimension of the value of your cross product is saying, which is, let's say cx, you're saying your ay times your bz, that times is not dot product, it's like normal. I think is it dot product? I think, yeah, it's a dot product. Right? So you have it operating on your bz minus your az, operating on your by, right? And so on and so forth. But Feel free to skip this, but try to take a look at it and try to look at it from the collab that I had sent to you guys, right? The collab gives a more visual, makes you understand it more visually, right? So everything I have drawn, you begin to see it play out, right? So the plot is already 3D, so it should make sense. I'll quickly introduce matrices and then I'll stop there for today. Yep, I'll stop there. So I have like 3 more minutes. So matrices are different from vectors, right? And my happiness is that you all understand how vectors work. Matrices are not too different, right? The only difference is that as against vectors where you're plotting a vector and it's pretty much you can see it, you can see vectors on a 2D coordinate, right? As a line, right? Matrices are 2D and you can visualize them on 3D, on a 3D space as planes, right? So when I say as planes, I mean, you could see it as a rectangle, you could see it as a triangle, which is something I had said before. And just like in vectors where you have row and column, this time around, the row or the column, none of the rows or the column is going to be 1, right? So you'll have something like this, where the shape of this matrix is 2 by 2, because you have 2 rows and 2 columns, right? Does this make sense? Does it make sense now? Anyone? Based off what you understand in vectors, does this make sense now? Okay, I would assume everyone understands what I just said, right? Yeah, so you have another kind of matrix that you call a rectangular matrix where, so the first one we had seen is pretty much like a square matrix. It's like the same number of rows, same number of columns. But you could have situations where you have your rows and your columns are different, right? And you'll call that the rectangular matrix. Right. In this case, can someone tell me the shape of this matrix? Okay, I have 10 minutes, so it's a good enough time. Thank you. That's like 6 more minutes. A 2 by 3, right? Cool, makes sense. You see that everything is making sense. I don't even need to explain too much, right? So now you have a diagonal matrix. So a diagonal matrix is one such that the non-diagonal elements are 0. So when you say diagonal, think of it as you are looking at values from the left to the right diagonally. That's what you call the diagonal matrix. And every other thing outside the values from the left to the right diagonally is 0, right? So think of it as, you could also have it as 1, 2, 3, right? And this is 0, 0, right? So pardon the way I'm writing. My writing is not, that's expired. 0, 3, 0, 0, right? Makes sense, yeah? So this is also a diagonal matrix. Yep. And again, you may not need it now, which is fine, but it's good to know what it is, because in future you're going to need it as a gadget to do some things, really. There's also an identity matrix, right? Where diagonally it's all 1, right? But every other place you have in 0. And the reality, the idea of identity matrix is that anything you multiply by an identity matrix, right, will give you the matrix itself. So think of it as you're saying 2 times 1 is equals to 2. Do you get? So an identity matrix when you do the dot product of an identity matrix with another matrix, it just gives you the same matrix, right? And then you have 0 matrices, which is also very, 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 very important when you're dealing with in your programming, right? Because you might need to construct a matrix from scratch, right? You might need to construct a matrix, put values in certain positions in that matrix. And it's usually a nice practice to create like some zeros matrix or some ones, right? Matrix, and then you begin to put your values into them, right? This my arrangement is scattering on, right? So similar to vectors and similar to your normal scalars where you have 2 times 1, 2 times 2, or 1 plus 1 is equals to the same thing as 2 plus 1. Yeah, matrices have their own kind of laws and the rest of it, right? Where you see there's a distributive law over addition, right? As you would see. So if you say a matrix A multiplied by some B matrix plus C matrix is the same thing as your A matrix times your B matrix plus your A matrix times your C matrix, right? And then there is associativity, right? Where you're having A multiplied by BC gives you AB multiplied by C, right? However, unlike in vectors, it's not commutative. So it's not always a case where you would have your A times B will be equal to, I have 2 moments, your B times A, right? And then you have transpose also in your matrices, right? So please tell me everyone understands transpose in matrices based off what we did before. I just need someone to tell me yes, and I'll be happy.
Yes.
Beautiful, right? So cool. Now, if we go further down, right, you see we have addition, we have subtraction, and then we have dot product, which is like multiplication. In matrices, you don't have cross product, so forget about cross product. So we're just, everywhere I did a product here is just your dot product, right? So similar to vectors, right? And just as you would see when you go through the Colab, which I encourage you all to go through, right? You'll see that it's pretty much the same as your element-wise addition, right? Element-wise subtraction, right? And the dot product is a bit different. Maybe, yeah, let me use the next 1 minute to do that. So you remember where I was saying row, column, row thing, right? And then I kind of gave you guys an idea of what it looks like, right? Let's see if it makes sense here. So imagine you have this guy, and this guy, right? And we want to do the dot product. The shape of this guy is a 2 by 2. That's this one here. And the shape of this guy is also a 2 by 2. So remember I told you that for you to be able to do the matrix multiplication, right, this 2 needs to be same, right? So it invariably means we can do this. And remember when I told you something about row times column, row times column? Again, it happens that happens here, right? So think of it as you have some vector here. Take this first guy. Take this first one first. Let's take this guy first, which is 1, 2, right? And it's operating on 4, 6, and 5, 7. So if we take this as a vector also, it means we are going to do what we did before, which is this times this, plus this times this plus this times this, which is just your 1 times 4 plus 2 times 6. So take it that this is just one position, right? Right? Now we do the same thing for the next column, right? 1 times 2 plus 1 times 5 rather, plus 2 times 7, which is going to give us what? It's going to be on the next side, right? 1 times 2, no, so 1 times 5, right? Plus 2 times 7, right? Yep. And then we bring in the next guy that we were not looking at before. This. And then we do the same thing, and we do it such that 3 times 4 plus 4 times 6, right? And then we have something here also, right? It turns out that what we have is going to be just like you have seen in the stuff. It's 16, 19, 36, 43, right? This is what we have. And you find out that the dimension of this guy is a 2 by 2. So what it means then, therefore, is that what it means, therefore, which is like the most, if this is what you take out from this whole lecture, I'm very happy. What it means, therefore, is that if you have a matrix M by N, and you multiply it, you do a dot product with a matrix N by P, the resulting shape of the matrix you would get is, can someone tell me what it is? Based off what you've just seen now, I know I've gone past time, but can someone just tell me, please? Okay, so I'll just say it because of time. It's going to be an M by
M.
Right? So remember we said 2 by 2 and the 2 by 2. Think of it that this 2 and this 2 cancels out, and you are left with 2 by 2. So question, if we have a 2 by 3 multiplying a 3 by 5, what will be the resulting shape?
Two by 5.
2 by 5, cool. But if we have a 2 by 3 multiplying a 5 by 2,
Is that meant to work? Do you think that should work?
you said?
The shapes are not together. I don't know, 2 by 3 and 5 by 2.
Can we transpose the first one? So it gives us 3 by 2, then we multiply it by.
Okay, let's try that. 3 by 2.
No, transpose the second one.
And 5 by 2. Doesn't still work, yeah?
Yes, but if you transpose the second one,
I think we'll transpose both of them. 2 by 3 and
2 by 5.
Okay, so we transpose this guy to right 3 by 2.
And then 2 by 5.
5. Makes sense, yeah?
We have
Or
3.
very simply, you just say if this is A and this is B, is B times A. Right?
Yes.
Because where did I do that?
Yeah. I get that. Yeah, that's true.
But I thought for matrices, B times A is not the same as A times B.
Yeah, I agree. Right? Not always the same. But think of it that I'm trying, when you're doing it in practice, right? Moving it around means something. This is just like, think of it as we are just trying to understand your this whole concept of shapes. Like I said, if you don't get it correctly, or if you don't understand the whole idea of this whole shape dimension thing, right, it's going to be problematic. So think of it that what we want to do now is it's pretty much understand how to play around the shapes to get the output that we want, right? However, when you're going to be doing an A times B times a B times A, the meaning means something. So think of it as think of it as you have X, Y, Z as a matrix, and you have also X, Y, Z as a matrix, Y, Z as a matrix, right? What we want to do, let's say what we want to do, right, is we want to do, instead of maybe if we're going to operate on this, right, what it means is that your X, Y, and Z is going to be operating on XXX, right? XXX, right? And think of it as a 3x3 matrix, right? Now, what if what we want to do is we want XYZ to operate on XYZ? Then it does not make any sense again. Doing this, right? Doing this particular operation doesn't make any sense again. So we have to transpose this guy, right? Or transpose this guy to get the result we want. Make sense? Okay.
So if we transpose either of them, we're still going to get a 3x3 shape. So when we want to multiply.
Yep. You still have a 3x3 shape, but the question is, what is within the 3x3 matrix? What is operating on what in the 3x3 matrix? So, you know, I had said, hold on, right? Think of the values now, right? Okay, one second. So, yeah. You have your X, Y, Z, right? The values here mean something, right? And the values here mean something, right? What if your goal was such that you want your X to multiply your X and your Y to operate on your Y? If you just do a row by column here, what you will have instead is your X multiplying an X, and then an X multiplying a Y, and then an X, or let me put it the other way so it makes sense. Your Y multiplying an X, and then your Z multiplying an X, right? But if you transpose this, let's say you transpose this guy, for instance, and it becomes, or you transpose this instead. Let's transpose this instead. And it becomes, instead of an XYZ like this, you have an XYZ. What you'll now have is an X operating on an X, and a Y operating on a Y here, which was previously here, and a Z operating on a Z, which was previously here. I don't know if it makes sense. I've gone way past time. So I have like an example to explain that in the collab, right? Where you kind of see where the numbers make sense, or where it makes where it means something. So even before the class, the next class we are going to have after the poll on Discord, right? What you guys can do is take a look at the note again, right? You can even read through. Okay, says makes sense now. Oh, nice. You can even read through the slides, right? I try to make it as simple as possible, right? And you see that putting it side by side with what you have on the collab will just bring sense, kind of make everything make sense, right? And understanding it conceptually, like from these basics, would make everything you're going to do in code relatable. It's going to make you understand the errors you see. It's going to make you see make sense out of the matrix multiplications that you're going to be doing later on in future, such that you take, for instance, you are working as an actuary in a company and they say you should calculate the probability of demise, or do some operation on the premiums, and you just should be matrix multiplication. Matrix multiplication will give me the answer sharp now. And you just multiply it without understanding what it's operating on what. and what your output is going to be, right? If you do that, it's going to be very catastrophic. You might find out that either the business bills people more than it should bill, all right, or the business loses more money by giving people very, very low premium or something like that, right? So this basically everything here is what I've done. And then I'll talk about determinants and inverses, right, in the next class. Take a look at it because it's very interesting. Everything we've done here can be used to solve your simultaneous equations that we already see. It looks like it's one gibberish stuff, but trust me, when you look at it carefully, it's the same thing as your 2x is equals to 5. What is x? That is basically what it is. That is basically what it is, right? So yes, we'll put the pool and yeah, when we go through, when we fix the time, we go through matrices, determinants, and then we go through sparse matrix, and then that's it. Right. Cool. And already, based off what you know, so if you go to the notebook, I don't have the notebook on my PC. Just give me 1 second. There is like a play. I've kind of created like a play section for you guys to play around things based off what you know now, right? You don't need to. It's not dependent on your understanding of it's not dependent on your understanding of determinants and the rest of it, right? Based off what you know now, what I would want you guys to do is this. And please, when you do it, I need you to post your results on the Discord channel. I want to see the output of what you people have done, right? Cool. So this is the notebook here. Okay. So if you scroll down, you'd see there is a place where I say, let's play, right? When you run this code, it pulls Laddie's picture. And that's why we looked at Laddie's picture from the beginning. In fact, let me just run it. This is just the last thing though. I need you guys to really play with this stuff, aside from playing with the other stuff at the beginning. All right. And those who know me, they know I like play. I so much like play. Shadrach knows now. Wait, we're on live. Hey, I got me. Okay, so what you find out is that pictures are just also some matrices, really, and they have 3 dimensions, right? The height, the width, and then the channel, really. And those 3 dimensions are just basically matrices stacked upon 2D matrices stacked upon each other, right? And if pictures are matrices, it invariably means that pictures are manipulated to get some output, right? Whatever they are operating, whatever you operate on the pictures, pretty much changes the behavior or changes the outcome of the outcome, which is also a matrix, is going to have some different shape or dimension or something, right? So pretty much, if you here I have written the code for you guys to plot the images. So there is a plot in 3D where you have the color channel, right? So a picture, the one that has colors, and then there is a plot in 2D, right? So what I want you guys to do is taking this picture as a matrix. So when I say as a matrix, you find out that image array is corresponding to this colored matrix, and gray image, this variable here, is corresponding to this black and white picture, right? These are just basically arrays now. I now need you guys to play around with these pictures and put the output in Discord. You can decide to use another picture, maybe your own picture, right? And let's see what the outcome is going to be. I can give you an example. So take, for instance, I copy this code, right? And I say, I want to play with Laddie's picture, and I multiply it by a scalar, for instance. And please don't do dot product with 3D, right? It's going to stress you for now. Just use 2D, or if you're going to do 3D, just do scalar multiplications. If you're going to do 2D, then you can do matrix multiplications, right? And 2D is just, your grayscale is basically 2D. So if I say I want to multiply it by 2, right? What's the output going to be like? So you see that it changes, right? So invariably meaning that if it's an array and I'm applying a scalar, it means the scalar is having an effect in the 3-channel dimensions, right? So play with this, show me what your result is. Then secondly, for those of us who are into actuarial science and the rest of it, I have a question here. You know, I had already said transpose and not transpose, right? There is something that happens one way or the other, right? Now think of it that you have this guy, you have this table, and you want to quickly apply a risk factor, right, to each and every of the row, right, of this table, invariably meaning that each of the row is corresponding to some group of individuals. Or so again, this is dummy data. Nobody's age is 856, please. It's just dummy data, right? So think of it that you want to apply a risk factor to all these rows, right? And the risk factor is given by a value from as you have here, right? How would you efficiently do this without writing this on paper or using a for loop? What can you use? Where does dot product come into play here, right? Do this and then put your results on the channel, on the Discord channel. If you have issues, please put it on the Discord channel and let's see what we can do. Make sense, yeah? I'm so sorry for the delay, for the time I took. I dropped the mic here. Thanks.
All right. Thank you, Kenechi. It was a long class, but I'm sure it was interesting. So guys, make sure to interact on the Discord channel, play around with the notebook, and also, you know, fill the pool so we know when you want to have the class to complete what we've done today. So yeah, you guys have like 30 minutes before you're allowed. So sorry for
30 minutes. I'm so sorry. Jeez. I'm so sorry. Okay.
Well, yeah, let's wrap it up and yeah, see you guys in your lab.